Hello, this is part 6 of my video playlist about the preparation of alkynes. This video is about the synthesis of alkynes by isomerization and by alkyne metathesis. Alkynes are usually easier to isomerize than olefins because alkynes are more acidic and less stable. However, allenes or conjugated dienes can also be formed, and it will have to be checked case by case if isomerization is a viable approach to a given alkyne. The examples in this video should help you estimate the likelihood of success. Catalyzed isomerizations usually yield the thermodynamically most stable isomer. Typical catalysts are bases and various transition metal complexes. Internal alkynes are generally more stable than terminal alkynes, and simple terminal alkynes can often be isomerized to internal methyl alkynes, as in the first equation shown here. The energy differences between terminal and internal alkynes and allenes are small, however, and the outcome will depend on the exact structure of the various isomers involved. If an internal alkyne is treated not with catalytic quantities but with an excess of a strong base, it is sometimes possible to obtain the terminal deprotonated alkyne. Because of the high acidity of terminal alkynes, this is the thermodynamically most stable isomer after complete deprotonation. Let's check some specific examples. 1-pentyne, for instance, could be isomerized by heating with less than 1 equivalent of ethanolic potassium hydroxide. The main product was 2-pentyne, and only 3.5% of an allene was formed. In this example, despite the large amount of potassium tersbutoxide, again a complete isomerization to an internal methyl alkyne occurred. Here, the reaction already proceeded at room temperature and was finished after 3 hours. In this example, the starting alkyne was particularly acidic, and stirring with ethanolic sodium hydroxide at room temperature led to the formation of a conjugated internal diene. Just for the sake of completeness, this is a rather weird isomerization of an enone. Gold and silver catalysts somehow transferred water from one enone to another without the formation of 1,3-diketones. Synthetically more interesting is the isomerization of derivatives of propargylic amines and alcohols. The outcome of these reactions again depends on the precise energy of the various accessible isomers. In the first example, treatment of a propargyl phosphorus amide with sodium hydride gave a mixture of an allene and an internal alkyne. A propargylic carbamate, however, mostly yielded an allene when treated with potassium tersbutoxide at room temperature. Here, a propargyl ether was isomerized to an allene with catalytic cesium hydroxide under mild conditions. Terminal alkynes are sometimes obtained in high yield by isomerizing internal alkynes with an excess of a strong base, typically alkali amides. In this instance, a mixture of sodium hydride and ethylene diamine was used, and the reaction was complete after 1 hour at 60 degrees Celsius. As described in parts 2 to 5 of this video playlist, terminal alkynes readily undergo C-C bond forming reactions and are therefore versatile intermediates for the construction of larger carbon frameworks. Even dienes can sometimes be isomerized to terminal dienes with an excess of a strong base. If solutions of lithium or other metals in amines are used, it is important to add the alkyne when the metal has finished reacting with the amine. Otherwise, the metal might reduce the alkyne to an olefin. I'll show you now some examples of alkyne metathesis. These reactions are catalyzed by metal carbene complexes, typically of molybdenum, tungsten, and rhenium. Like olefin metathesis, alkyne metathesis proceeds by sequential 2+2 cycloadditions and cycloreversions and tends to yield the thermodynamically most stable product. The direction of such reactions is sometimes controlled by evaporating a volatile product. Most reported examples involve internal alkynes, because terminal alkynes can form stable, unreactive complexes with the catalyst. This here is a typical example. With 10% of a bulky molybdenum-carbene complex in toluene, a methyl alkyne was transformed into a symmetric internal alkyne and the volatile 2-butyne. The primary tosylate remained unchanged. Some newer catalysts are even compatible with unprotected hydroxy groups. Here, octinol underwent metathesis with only 5% of a molybdenum-carbene complex. If a difunctional starting material is to be cyclized to a large macrocycle, you'll usually require high dilution to suppress oligomerization. In this example, a metathesis catalyst was generated in situ from 2-fluorophenol and molybdenum hexacarbonyl. With this catalyst, dipentenyl succinate could be cyclized in high yield to a 12-membered cyclic diester. In this example, a still larger lactam was prepared by ring-closing metathesis at high dilution with a rhenium catalyst. Ring-closing alkyne metathesis has also been applied to the synthesis of structurally sophisticated natural products. Here, the target cyclic alkyne was obtained in high yield, but 25% of catalyst and high dilution were required. Olefins do not react with carbene complexes and are compatible with alkyne metathesis. Both the terminal vinyl groups, like in the previous example, and even internal cis alkenes remain unchanged. Here, a macrocyclic lactone was prepared with only 5% of catalyst. Let's have a look at some potential side reactions. Alkynes, like reactive olefins, readily oligomerize, and during acid or base-mediated isomerizations, dimers or trimers are sometimes formed as byproducts. As shown here, treating 2-butyne with aluminum chloride yielded a cationic dimer, which could be either isolated or converted into a trimer with an excess of butyne. Metathesis catalysts can also bring about cyclotrimerizations, as in this example. These are usually catalyzed by cobalt, but molybdenum also seems to work. Here are some further examples which you can also find in the description of this video. Under the Community tab of my channel, you'll find a PDF version of the slides. The next video of this playlist is about the generation of arynes and strained cycloalkynes, and about the reactivity of these intermediates. See you then!